I've made a change to homework 5. That's the assignment that's due on Tuesday of next week. If you've already looked at homework 5, there were originally 8 problems, and I've moved the last one of those homework problems onto homework 6. So I've posted a new PDF file that only has 7 problems on it. We're only going to get part of the way into the Euler's equation today, so I moved the more difficult of those Euler's problems onto the next assignment. So those 7 problems are due on Tuesday before class. I'll be checking my email over the weekend if you have questions on it, or you can stop by my office. I'd be glad to go over anything that you need help with. Today we're going to talk about convective acceleration, continue the example that we didn't get to in class on Tuesday, and then we're also going to discuss Euler's equation. Any announcements, questions? Okay, here's where we left things last time. We were looking at a nozzle, and the nozzle was accelerating the fluid as a function of position. What we're looking at, I'll just say it's a steady flow. Conditions aren't changing over time, but what's happening is that there's still an acceleration. The velocity into the nozzle is less than the velocity coming out, and so therefore, something about how it moves through this shape is causing the velocity to go up, and therefore there's an acceleration. The type of acceleration that occurs during non-uniform flow, like this, is convective acceleration. So what we're going to do is we're going to find out what is the convective acceleration at the midpoint in this nozzle. And what we're given is an equation that describes the velocity as a function of position. L is the entire distance from one end of the nozzle to the other, and x is the direction that we are traveling, the fluid is traveling in. And at the midpoint, if the overall length is 0.5 meters, the midpoint of 0.25 meters here in the center is where we want to find the convective acceleration. Now, convective acceleration, a sub x, meaning the acceleration as a function of position, is the velocity at a certain location multiplied by the change in velocity with respect to position at that location. So here's our function that describes the velocity, and what we're going to do is apply the chain rule to find out the convective acceleration at the midpoint. So we want to find out for a given velocity what is du dx. And the chain rule says that du dx is du dm by dm dx. And by m, we can assign the denominator of our velocity equation to be m. So I'm going to call m 1 minus 0.5 divided by L. So that gives us that the velocity is the initial velocity divided by m. So this equation that's on the screen here, the velocity as a function of position is just going to be the initial velocity divided by this new pseudo-variable m that I've defined. In other words, we could say that's the initial velocity times m to the minus 1 power. So du dx is d of du m to the minus 1 dm multiplied by d of 1 minus 0.5 x divided by L with respect to dx. Okay, so we can do that. The derivative of the initial velocity m to the minus 1 power is just going to be minus 1. The initial velocity m to the minus 2 power And if we take the derivative of this function with respect to x, what we end up with is just 0.5, negative 0.5 divided by L. So that's the result. And then remember our definition of what m was. That m is 1 minus 0.5 x divided by L. So du dx is minus 1, the initial velocity, divided by 1 minus 0.5x divided by L to the squared, multiplied by negative 0.5 divided by L. So I've just resubstituted in what m is. So if m is this, I'm just putting that back in after having taken the derivative. So over here is where I've substituted back in our definition of m. And so aggregating that together, we have 0.5 times the initial velocity u naught, L times 1 minus 0.5 x divided by L squared. Now, the position that we're interested in is the position of 0.25 meters. So x is 0.25 meters, and L is 0.50 meters. So we'll substitute both of those given dimensions in, and simultaneously we want to know u du dx, because that's the convective acceleration. So a sub x is going to be 0.5 u naught squared divided by 0.5, 1 minus 0.5, 0.25 divided by 0.5, and all of that is cubed. Because we have multiplied u by du dx. Okay, we can simplify that to be u naught squared divided by 0.75 cubed. So 1 minus 0.25 is 0.75. The 0.5 in the numerator and the denominator cancels out. So that's 2.370 u naught squared. And we actually know the initial velocity. That's given from the diagram to be 10 meters per second. So u naught is 10 meters per second. So the acceleration, the convective acceleration, u du dx is 2.370 times 10 squared. So it's 237, and the units for acceleration, convective acceleration has the same units as local acceleration. It's meters per second squared. So that's the rate of change of velocity at the midpoint of this nozzle. I'm going to bring that file up so that it's captured in the recording.
How did you get the 2.370?
That is 0.75 cubed, and it's in the denominator. So if you divide 1 by 0.75 to the third power.
Oh, okay.
Okay, so if you need to look at that another time, here's the solution up on the screen. On the homework assignment, I think that you have maybe 2 problems that are related to convective acceleration. Remember that convective acceleration is what causes velocity to change with respect to position, and so that's non-uniform. So local acceleration is associated with flow that's changing over time, so that would be unsteady flow is local acceleration. Convective acceleration is associated with non-uniform flow. Like I just mentioned, steady is when velocity is constant with respect to time. Uniform, velocity is constant with respect to position. So local acceleration is what causes a change over time. Convective acceleration is what causes a change as the fluid moves through positions. And so you can see steady versus unsteady, uniform versus non-uniform. Today we're going to talk about Euler's equation, which is an application of local acceleration. And then next week, beginning on Tuesday, we'll also talk about Bernoulli's equation, which is the application of fluid acceleration that's caused as a fluid moves through space. So it's associated with convective acceleration. So today when we're looking at Euler's equation, just keep in mind that Euler's equation is applied when there's local acceleration. So you use it if you have unsteady flow. You use Bernoulli's equation when you have non-uniform flow. We can make a table, a 2x2 table that has steady versus unsteady, uniform versus non-uniform. And this kind of illustrates that you can have steady, uniform flow, and that's the easiest thing to calculate. You know, when we're doing hydraulic design, we really like it when conditions are steady and uniform because we don't have to think about the velocity getting changed from one time to the next. And if we have a straight uniform channel, then there aren't going to be any changes in flow having to do with the diameter decreasing or increasing. Steady uniform is the simplest case. And then we have unsteady flow that's uniform. So that means maybe there's a nozzle on a pipe that's gradually opening or closing that's causing the velocity to change over time. So that's uniform flow that's unsteady. You can have steady flow that's non-uniform, meaning that over time things aren't changing, but the velocity does change through position. And so this is a contracting nozzle where you can see that there is an acceleration having to do with the shape of the nozzle and the movement of the fluid through that confining diameter. But the most complicated case is when you have 2 kinds of acceleration happening simultaneously. You can have the fluid accelerating both because the flow conditions are changing over time, and the flow can also be accelerating with respect to position. So if you have a contracting nozzle, which accelerates the flow as it goes from left to right, but what if you're also opening up a nozzle and increasing the velocity over time? Then you'd have unsteady, non-uniform flow, and to predict the pressure change, you'd have to use Euler's equation and Bernoulli's equation simultaneously. So that would be a more complicated scenario to predict the pressure difference between the opening of the nozzle and the exit of the nozzle if you had it experiencing 2 simultaneous forms of acceleration. Today we'll just consider Euler's equation, which we use for local acceleration. So it's used to model pressure changes when fluid is accelerated, and you already have something similar to Euler's equation because the hydrostatic equation tells you the effect of acceleration on a pressure change. The hydrostatic equation is saying that there is some pressure difference as you move down through the fluid because this fluid is experiencing gravitational acceleration. That's what the acceleration is in the hydrostatic equation. In Euler's equation, we're building on that same idea that acceleration causes pressure differences, and what we're building is we're building in some additional acceleration beyond gravitational. And I think I changed the phrasing in the notes. If you've got the notes printed out, what did I have written there before? Other than gravitational? I changed it to say in addition to gravitational because Euler's equation already considers the effects of gravity. And so it can handle gravity and another acceleration at the same time. So I think in addition is maybe more clear language to describe what Euler's equation is doing. So hydrostatic equation, if we had the tank that was just motionless, like if you just had a tank of water sitting there, the way that you predict the pressure, 1 meter down into the tank, you just say delta H is 1 meter, gamma is 9810 newtons per meter cubed, and so the delta P for a stationary tank delta H times gamma would be 1 meter times 9810 newtons per meter cubed. So 9810 newtons per meter squared is the pressure at a depth of 1 meter when it's being accelerated by gravity. But what if the tank is being accelerated upwards? Like maybe this tank is in an elevator, and the elevator is gaining speed. It's moving up and it's accelerating. So the idea is there's going to be even more pressure at a depth of 1 meter than there otherwise would have been if it was stationary, because the fluid is experiencing gravity and also some additional acceleration on top of it. This equation is kind of a simplified version of Euler's equation that you can only use if the acceleration is vertical. You can't use it in other circumstances if the acceleration is sideways, for instance. But if the acceleration is in the same direction, in the same vertical direction as gravity, then what we could say is that the delta P is going to be 1 meter times the unit weight of the water, or just if we're keeping the density separate, so 1,000 kilograms per cubic meter, and we're adding the two accelerations together. The 9.81 meters per second squared due to gravity, and then the 9.81 meters per second squared of additional acceleration. So the delta P in that case would be 19,620 newtons per meter squared. What would be the pressure 1 meter down if the elevator was accelerating downward at G? It would be 0, that's right. And so that means that a glass of water in the space station, if you had a pressure sensor and you put the pressure sensor into the water, it's not going to register a change in pressure in the same way that if you had a really sensitive pressure transducer and you put it at the bottom of a glass of water, you'd measure an increase in pressure here on Earth. But where there isn't a gravitational acceleration, then there won't be a change in pressure. I kind of resist showing this to people because unfortunately sometimes people don't get the warning. I made it bold this year. Maybe that'll change it. But sometimes people use this equation in situations where there's like a sideways acceleration, and it just doesn't work when the acceleration is sideways. We have a more powerful equation that's always valid that we can use in other circumstances. And the origin of Euler's equation is just the idea that the sum of the forces is equal to the mass of a fluid element multiplied by the acceleration that it experiences. And so consider here is a cylindrical shape, and it's just a cylindrical element of water that's being accelerated in the L direction. And here this diagram shows us that the L direction is it has horizontal acceleration, and it also has a vertical component. There's 3 dimensions here, and I think that this L that they're talking about is simultaneously experiencing horizontal and vertical acceleration. So there's some pressure that you could measure at the bottom edge of that cylinder, and if you go some distance delta L in the direction that it's accelerating, then there'd be a different pressure. There'd be the original pressure plus some change. And the delta A that they're talking about is just the cross-sectional area of that cylinder. So if we do a force balance and we consider the weight of this element of water and we consider the acceleration that it's experiencing, then we can account for the change in pressure by the acceleration that it's experiencing. P times A is a force. And so there's a force pushing this way. There's a force that's opposing it on the outside of that fluid element, and the force is different because the pressure is different. And the difference in pressure can be attributed to the acceleration that it's experiencing. The questions that we ask when we're solving problems like this is how much fluid do we have? It'll usually be like a tank of water that's experiencing acceleration in these types of problems. And we'll need to see if any information is given related to the difference in the forces that's being applied to cause the acceleration. The 2 factors that's causing a change in pressure is the gravitational effect, which is acting downward, and then the acceleration in the L direction. So there's 2 accelerations that's happening simultaneously. G is acting down, but then there's a separate acceleration that is in the X and Z direction. And so if it's going up and to the right, then we'd expect the pressure on the bottom side of that cylinder to be greater. The pressure increases in the opposite direction of acceleration. So in the case of this tank of water, if we put it on an elevator and the elevator is accelerating up, then the pressure increases in the opposite direction. It's getting even more pressure at the bottom of the tank than it was before, as the elevator causes it to accelerate upward. Okay, here's Euler's equation as it's written on the equation sheet that you have for exams. And the reason why it's written this way is it's generalized for some direction L. And what you'll usually need to do is transform Euler's equation and apply it in whatever direction the problem tells you the acceleration is occurring in. So the way that you kind of expand it out so that you can actually start substituting values, you can't just put the numbers into this form of Euler's equation. What we will assume is a linear variation in pressure between 2 points. So it goes from one location to the next is where you'll apply Euler's equation. It's going to predict how the pressure changes between those 2 spots. So if we say that the acceleration is occurring in the X direction, so horizontally, then we'd say that there's some change in the piezometric pressure between the 2 points that are delta X apart. So if the X is the direction of the acceleration, then the 2 points, you need to measure how much X separates them. We'll get plenty of practice solving problems like this, but you'll find the distance apart they are in whatever direction the acceleration occurs. And then you'll notice here is a density parameter related to whatever the fluid is and the acceleration in that direction. So this is the further transformation. When I say we're applying this at 2 points, usually the way it works is you'll be given a measured pressure at one location, and you need to apply this Euler's equation to predict what the acceleration is going to be at the other location. So we've rearranged this. You can see that the delta x is now moved to the right side of the equation. And by delta P plus gamma z, that's piezometric pressure. The delta piezometric pressure is the piezometric pressure at location 2 minus the piezometric pressure at location 1. Now location 1 and location 2 has a very specific implication. There's a convention that you have to use and be consistent with, otherwise you'll get the wrong pressure. And what we mean is that we're going to assume that if we have 2 points and one is further to the right than the other, then the one that's further to the right we're going to call location 2, and the one that's further to the left would be location 1. So it doesn't have to do necessarily with which one of them is above versus below if the acceleration is in the horizontal direction. Now if the acceleration is vertical, then yeah, you have to consider which one has more z. The point that has more elevation you'd call location 2. So we'll get some practice following that convention, but on problems like this, the most common mistakes that I see is students who try and substitute numbers into this equation, which you can't do. You have to expand the equation out with the assumption of a linear pressure variation between points. And then the other mistake is flip-flopping which is location 1 versus which is location 2. All right, so let's take this truck as an example. And let's say that it is experiencing an acceleration to the left. So it's slowing down at a rate of 3.05 meters per second. So if it's slowing down, then that means that the acceleration is 3.05 meters per second, and that's in the negative x direction. The truck is carrying gasoline. So we have a different density and we have a different unit weight than we'd normally use. Note that. And then the other thing is we know the pressure at a certain location. Here at the top left edge, I'm going to call that location T. We know that the pressure is 0. So as it slows down, just think about what happens to you when you're in a car that's slowing down. You feel the pressure of the seatbelt on your chest, right? Because your body it's going forward. It wants to continue going forward. So to slow you down, something has to be pushing against you in the opposite direction. So here, the water, no, it's gasoline. The gasoline is moving to the right, and it wants to continue moving to the right, but the truck is slowing down, so the truck is pushing the gasoline to the left to slow it down. So if the acceleration is to the left, then the pressure increase is the opposite direction. So the pressure is increasing to the right. That's a general rule that you can write down and always keep in mind, is that the pressure increases in the opposite direction of acceleration. All right. So what I'm going to do is I'm going to set up Euler's equation on the board, and we'll talk about which is location 1, which is location 2, and then I'll ask you to go through and substitute it in to find the pressure at point A.
Is the density 0 or?
The density of the gasoline?
Yeah.
No. You can calculate the density of the gasoline by the unit weight divided by G. So if the gasoline is 6,600 newtons per meter cubed, and you divide by 9.81 meters per second squared, then the density is 672.8 kilograms per cubic meter.
The reason I say that because there's like a P up there where T is, but I can't tell if it's a.
That P means the pressure.
All right. I can't tell if it's density P or where the pressure P.
Right. Yeah, that's a pressure P. It's not rho. Okay. So so the acceleration is negative 3.05 meters per second squared. You have to have the negative sign when you substitute it into Euler's equation to go along with our convention that we have location 1 and location 2. And so location 2, when we use Euler's equation, is going to be A, because it's further to the right. In problem 1, we're comparing what's going on at location A to what's going on at location T. So A is 2, and location 1 is going to be T. So remember how Euler's equation expands is the pressure at 2 plus gamma Z2 minus the pressure at 1 plus gamma Z1 is equal to negative delta x, density, and acceleration in x. So what do we know? We know the pressure at T, and we want to find the pressure at A. So P2 is the unknown. Now what about Z? What's the elevation? Well, you can use whatever you want as long as you're consistent between the 2 points using the same datum. So you could use the bottom of the truck, the bottom of the tank as the datum. You could use location T as the elevation datum, as long as you're consistent between both points. So calculate what is the pressure at A if we know that the pressure at T is 0 kilopascals. What kind of acceleration is this truck experiencing? Local. Local acceleration. So it's unsteady conditions. Okay, so 12,517 pascals will be the pressure at that top right edge. And you'll notice that when we expand out Euler's equation, we're going to cancel out both of the z terms because we're on a horizontal plane. The 2 points of interest have the same elevation. So that term cancels out. And the other thing is that the pressure at this top edge is 0. So the pressure here at A is just going to be minus delta x, and the 2 points are 6.1 meters apart, the density, and then we have to be sure to put in the negative sign to denote that this is accelerating to the left. And so the minus and the negative sign in the acceleration will cancel each other out, and that tells us that we have a positive pressure at A of 12,517 pascals. Any questions about this one? All right, the example goes on to ask where is the pressure the greatest. So it's probably going to be one of the 4 corners, one of the extremes. So here, 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 or there. And so obviously it's not T, because 0 isn't the greatest, right? But the pressure at this bottom left corner is bigger than it was at T. So, there's some positive pressure down here at the bottom left. But where will the pressure be the highest?
B.
B. Wow, it's convenient that that's labeled there, right? Otherwise, how would we know what to call it? So location B is the point where it has the highest pressure, and so it's going to have all of the pressure that A did, but then it's also going to have a little bit more because it's deeper in the fluid than A was. And so it's experiencing that same effect having to do with the deceleration. Part of the pressure at B is due to that, But part of the pressure at B is also due to the fact that it's lower than location A. So it's going to be the 12,517 plus 1.83 meters of this gasoline. So the vertical dimension there, 1.83 meters multiplied by 6,600 newtons per meter cubed. So there's going to be an additional 12,078 pascals of pressure having to do with, I guess we could call it the hydrostatic effect, even though it's gasoline, not water, but because in the vertical plane, there isn't any additional acceleration. There's acceleration horizontally, but vertically, the only thing that's happening is G. So the total pressure at this second location, the total pressure at location B, we'd say is going to be 24,595 pascals. But let's look at it in a more robust way. You know, just adding on the hydrostatic force separately won't always be true because there might be a vertical acceleration. So if we just get in the habit of instead using the Euler's equation for all problems where there's a local acceleration, then we'll have the tools to use it to get the right answer anytime. So what we could say is we could use Euler's equation where we have the pressure plus gamma z at location B minus the pressure plus gamma z at location T is equal to negative delta x density acceleration in x. Now I'm doing this in the x direction because that's the direction that we have the external acceleration. Okay, so this means the pressure at B plus gamma ZB minus the pressure at T minus the pressure, minus gamma ZT is equal to negative delta x density acceleration in x. So what is the pressure at B is the question. So there's a few things that we can cancel out. This time let's have the datum be the bottom of the truck, like the bottom of the tank anyway. And so if the bottom of the tank is our datum, so we're going to z equals 0 here at the bottom, and at the top here z equals 1.83. The other thing that we know is that the pressure at T is 0, so we can still cancel that out. I'm going to cancel out the pressure at B term, since it's, the gamma ZB, because Z is 0. So the pressure at B is going to be gamma ZT minus delta x density acceleration in x. Euler's equation simultaneously accounts for differences in elevation and the acceleration that occurs. So here is the term that's accounting for an elevation difference between 2 points, and here is the term that's accounting for the acceleration that occurs. So it can handle it. The point is you don't have to like manually correct for differences in elevation. Even though these 2 points aren't at the same elevation. You know, T is above B, but location 2 was B, because B was further to the right. You know, when we have one thing, the piezometric pressure at one location minus the piezometric pressure at the other, the piezometric pressure, the first one, is going to be what's further to the right. So that's why we had B as the first term there. So if we substitute in those numbers then, it is 6,600 newtons per meter cubed. So 1.83 meters minus 6.1 meters, 672.8 kilograms per cubic meter, and negative 3.05 meters per second squared. So this first part is 12,078 pascals, and that's the pressure difference that's related to the elevation change. And then the second part is a positive pressure of 12,517 pascals, and that's the pressure change that's caused by the acceleration. And if we add them together, the pressure at B is 24,595. There's only like 5 or 6 equations that are going to come into play for the second midterm exam. Euler's equation is one of them. So it's important to keep track the direction notation, you know, which is 2 versus which is 1. Always pay careful attention to the sign of the acceleration. That's a common mistake that people make. And then keep in mind that in a single problem, you'll be putting in the unit weight and also the density. So you'll need to have both of those calculated for whatever fluid you're working with. Any questions about calculating the pressure at the bottom right part of the tank? Yeah.
Not on that, but are you able to like generalize this and say that you can do this at more than 2 locations in a fluid, or say like maybe use superposition and do it, you know, like 5 or 6 times up through?
That's a great question. I think I understand what direction you're heading. Let's say that we have, what if there's a tank of water that's being accelerated in 2 directions? So let's consider the case of you know, some tank of water that's experiencing an acceleration in x and also an acceleration in z at the same time. And we know the pressure here at A, but we don't know the pressure at B. The approach that we're going to learn in class on Tuesday next week is we're going to say that what you'd have to do to solve a problem like this is you'd have to pick an intermediate point. So I'm going to call this like M. So we'd go from A to M by considering just the acceleration in z, and then we'd go from M to B considering the acceleration in x. What we wouldn't be able to do is try and come up with like some acceleration in the L direction, you know, like this squared plus that squared divided by that. The square root. Yeah, like we couldn't use that and then have some length. You end up not getting things quite accurate if you try and go directly from A to B. You have to take the acceleration in each direction as it occurs. So we'll get some practice with that. But I hope that at least speaks to a little bit of what your question was. One other point that I'll make regarding the exams is I noticed that a lot of people who made mistakes probably could have avoided them if they had included the units there on the paper as they were doing the calculations. That's like a really good habit, in my opinion, to always write the units and not just the number. Now, the units aren't going into your calculator, obviously, but if you write the units on the page, then that'll help you to know if maybe you put the wrong thing in. Like if you're putting in centimeters instead of meters, or if you wrote in density instead of unit weight. Just including the units along with the numbers when you're solving problems is a way to avoid mistakes. And so I'd encourage you to do that when you can. Okay, that's all for today. Remember that homework assignment that's due on Tuesday only has 7 problems. I removed the 8. So I'll see you then.
On problem 4, I thought the force of the water above was a